Our main presenter today is no stranger to the Oasis community. He is a regular contributor to NPR's The Engines of Our Ingenuity, a nationally syndicated radio program. He's also an adjunct professor at the University of Houston Collins College of Engineering. So please help me welcome Dr. Andy Boyd.
Thank you. Good morning. Thank you. Let's start with the best part here. Is the microphone working properly? Good. Everybody here? Good. That's a good start. And also, I wanted to say, Hank, if he's here, I have the CD that song that he just played is on, so I can recommend that you can buy some CDs from him here. Okay. A man walks up to a scientist and says, "Your theory that the Earth is a great sphere floating in an immense cosmos is hogwash." "Oh," replies the scientist, "do you have a theory of your own?" "Yes," the man says, "and it's not a theory, it's the truth. We live on the back of a giant turtle." Prodding the man to think further, the scientist asks what the turtle rests on, to which the man replies, "It's turtles all the way down." Today we aren't really going to go all the way down, but I'd like to take a look at how crazy the world gets on the journey downward toward the infinitesimally small. Let me see here. Excuse me. I'll get warmed up. Oh, on a personal note, the things I'm going to share with you this morning are the reason I never finished a major in physics in college. It was so unbelievable that I thought I was missing something. What my physics professor needed to tell me was, let go of my preconceptions, because at an intuitive level, this stuff doesn't make any sense whatsoever. If he'd actually done that, I might have stuck with physics. What I needed to do was take a leap of faith into a world that was beyond my means to comprehend its physical reality. So bear with me for 20 minutes, and I hope I'll be able to take you down that same crazy road. As we get started here, I'd like to start off with a quick game. Can I get a volunteer? Come up here with me for a minute. Come on up. We all know. Stephen? Stefan? Stephen. Stefan. Okay. I'll let you just stand there for a moment. Now, I'm going to take, this is in fact a Houston Astros baseball. And it was purchased, I must say. So what I'm going to do is I'm going to take it from here, and I'm roughly here at the microphone. I'm going to walk it over here like this, maybe circle around a little bit, and it arrives here. Okay? Nothing exciting about that. Stephen, would you please do the same thing for me? Take it there, and you don't have to take it directly. You can kind of take a little route. I'm not going to watch. But you can just tell me when you get there. You don't have to take too long, unless you want to do something entertaining. You're there? Okay, good. Now, I like to do things to make the utterly obvious, okay? But I didn't have to see the ball move from there to there to know that it traced some path to get from there to there, right? I don't know exactly which path it went, but the alternative to it not following some path to get there is, I don't know what. It disappears and it reappears over there. So I just want to make a very simple point. Thank you, Stephen. I wish I had something more exciting for you to do. Yeah, could I give my hand, though? So my point is, I was trying to make the very obvious, okay? And there's usually a reason for that, okay? So moving on, let's imagine that we have a heavy box floating in outer space containing a perfectly elastic ball. We're told someone has set the ball in motion, bouncing back and forth between the left and the right sides of the box. So we open it up, and there we see what we'd expect. We remove the side of the box. We see the ball bouncing back and forth at a nice uniform speed. Nothing very exciting. I point out, if you can see that little line there in the middle, and it's hard to, it's a reference line. It's not really there, but it's supposed to be there to help you see it a little bit better. Okay. Before moving on, I just wanted you to take a look at that. Before moving on, I'd like to make a quick observation about speed and energy, and in particular, kinetic energy. Here I've got the ball traveling at two different speeds. The faster the ball is moving, the more energy it has, as you'd know if you stepped in front of it. Alternatively, the more energy the ball has, the faster it's moving. Again, I'm making a very simple point, but moving forward, it's going to become clear that I'm going to want to talk about energy and not speed, so I kind of wanted to just lay this out right now. Now, instead of a ball, let's consider some subatomic particle, like an electron in a box. The box is going to be a lot smaller because the electron's much smaller. But otherwise, this situation is going to be really similar to what we've got right here. So let's go down to that very small world and see what happens. Okay, the first problem is that we can't actually watch the electron tracing a path back and forth. Unlike the baseball, we can't follow it as it moves. It's almost as if when I was not watching the ball, that's what we're going to have to do. Now, the reason for that is it's due to something called the Heisenberg uncertainty principle. Though I'm not going to dwell on that this morning, we'll just take it as a fact. We can't actually watch the ball move, but we just can't do it. But while we can't watch the electron move, it turns out that if we look for it in an instant in time, we can see where it is at that moment. So what we're going to do is we're going to turn our electron loose with a fixed energy, just like we had our ball. And then while we can't watch it follow the path, we'll take a few snapshots and kind of see what it looks like. Okay, so here come a few snapshots. We're seeing the electron, different points along the path. Taking a few more pictures. Okay, I think we're about done. Now, does anything strike anybody as something that might be a little bit weird about what's going on here? Want to stand up and say it really loudly? Yeah. It doesn't seem like it's showing up at the middle of the box. And as you can see, it also doesn't look like it's showing up at the two ends of the box either, which seems somewhat problematic. Maybe we just took the pictures at the wrong time. But in fact, no. Let's take a look at this graph. We had already had probability thrown up there. But what this graph down below is showing is where it's more or less likely that we'll find the electron. So at a point up here, it's very likely. Okay, somewhere in the middle of this grouping up. Very likely we'll find the electron. Less likely, less likely. And in fact, it drops to actually a probability of 0 at both ends and in the middle. Okay. Now, where did this come from? Well, it comes from underlying mathematical theory that's been tested over and over again, not just on this experiment, but other experiments. So it's a well-developed theory over about 100 years now. So we're not just pulling this out of the box, and this is the way it seems to be working. So what's going on here? Is there a big question you might want to ask yourself? It's a question I asked myself in third semester physics as an undergraduate. How does the electron get from one half of the box to the other when there's no chance that it can be found in the middle? Okay. You know, to me it was like, I just don't get this. Give me back math. Math is perfect. So that's the question. So how does the electron get from one half of the box to the other? Okay. Here's some potential answers. One is that we don't care. And there's actually a certain logic to this. Since we can't actually watch the electron trace its path, why worry about how it gets from one place to another? We don't need to know how it moves in order to make scientific advances. In fact, we've been making advances with quantum theory without having to answer some of these more intuitive questions. We just keep working the math. Okay. So to a large extent, this is in fact how physicists answer the question as a practical matter. They just don't worry about it. It's not an issue. But you have to admit, it's a completely unsatisfying answer. After all, as we saw earlier with the baseball, just because we couldn't watch the path doesn't mean the electron doesn't follow a path. So if it's following a path, how does it get through that place where it can't possibly be? Okay. So that leads us, how could this be? So it's unsatisfying. So is there another answer that we can consider? Well, here that might be this other answer. The electron doesn't move, but instead exists in a shadowy world of possibilities until we observe it, at which point it shows itself. Okay, this doesn't, I want to make it clear, this doesn't just sound weird, it is weird. Though it does get past the problem of getting the ball from one half of the box to the other. But it raises all sorts of other problems. For example, isn't this like it's popping into and out of existence, if we're talking about a shadowy world? So isn't that kind of like it doesn't exist and then all of a sudden it does exist somewhere else? Okay? And there are other problems as well. Notice that what does it mean to observe? Is it a physical observation on the part of a human that causes the electron to reveal itself? Without the human, what does it mean to observe? Because if we weren't taking those pictures, where would it actually be? It seems if it's existing in a shadowy world until we observe it, then it's kind of floating in never, never land until we actually see it. But still, and this is interesting, at another practical level, physicists really do accept this interpretation, but they phrase it a little differently. A physicist might say, the electron exists in the superposition of all possible states until the act of observation causes it to collapse into one particular state. Now, I'm not sure how literally physicists take such statements, but they're used frequently because they're a good shorthand for describing the math and the experimental evidence. So you will read in most physics books about the superposition of the particle due to a wave function, and it collapses into a particular instance of it. So you will actually read this in books. Okay? So they use words like superposition and collapse because it avoids using phrases like shadowy world of possibilities and shows itself. But the meaning isn't fundamentally different. So let me stop here for just a moment to say the following. You should be completely and utterly bewildered at this point. And again, just to go back, when I saw this and I was trying to make physical sense of this, I thought I wasn't understanding something. And I really did. I needed my physics professor to shake me and say, you can't start understanding this stuff at an intuitive level because it just doesn't make sense at an intuitive level. And I wound up doing math. Okay, so moving forward, let me point out that this picture I showed earlier was for an electron at a single energy value, so kind of the equivalent of a ball moving at one particular speed. It doesn't always break into two parts. Let's see here. As we move to higher energy levels, we get the same type of picture, just with more peaks. So here's another energy level that's a little bit higher, and instead of having 2 peaks, we have 3, but we still have this problem of these 0 probabilities. And as we move up in energy, we can add as many peaks and troughs as we'd like, but they all have these 0 probabilities. It just gets to be more and more of a problem of how to get from of what's going on down there at that level. So again, just to make this clear, this was the less energy case that I was showing you. Here's a more energy case, and we could have more and more and more energy. So we're not limited in the types of energy that the electron can have. Okay, now let's go off to the side a little bit here. Imagine for a moment that you're behind the wheel of a car, okay? And you're starting at 0, and we're going to see how long it takes you to get to 60 miles an hour. We don't see that so much these days, but that used to be quite common. Car goes 0 to 60 in how many seconds? Okay. So you're sitting there, and I was going to say you put it in gear, but nobody puts it in gear anymore. You just step on the gas pedal. So you step on the gas pedal, and you start to feel a push back in the seat. And you go faster and faster and faster, and you're pushing hard. You hit 60 after some period of time. Okay. So to be just a little bit more specific, you get the idea. Here's the case of a Toyota Prius. And down here on this axis, I have time in seconds. And up here, I have speed in miles per hour. So we start off at 0, at time 0. And sometime later, actually a little more than 10 seconds later, we hit 60 miles an hour. Okay? Now, this line being straight talks about constant acceleration. It doesn't have to be straight. You know, if you're putting your foot on and off the gas pedal, it could wave. But it just kind of goes up through here like this until you reach 60. Okay? Let's see. So that's perfectly fine. And it does take a Toyota Prius about 10.5 seconds in economy mode to get to 60 miles an hour. Now, alternatively, we could take a Porsche, 2015 Porsche 918 Spyder, which, if you believe everything you find on the web, was the fastest car, car available to you and I, not a dragster, a road car. And it can do it in a little about 2.2, 2.3 seconds. And by the way, Teslas do this too. They're right up there too. If you get a Tesla and you put it in ludicrous mode, which in fact it does have a ludicrous mode, then you can about the same thing. Now, one thing about this is that a car moving at this speed, getting about 2.3 miles an hour, you feel it. You get pushed hard back in the seat. You feel the blood running to the back of your head. I have not done this in a Spyder, but I have done it in a Tesla, and it's really a remarkable experience. So you feel it, that acceleration, and you don't want to be driving unless you've had some practice doing that. I'm not saying you're blacking out, but you know it. And that's because it's accelerating much faster. This line is much steeper here. Now let me show you what, there are different steepnesses, but they're similar. But let's go to the next thing and make a point here. This is something that's impossible. Okay, so what we have here is that a car is accelerating, however, it's getting up to about 30 miles per hour, and then it jumps to 40 miles per hour with no time break at all. Okay, so you can think about it. It would look visually weird. You'd see this car going along, and then you can do it. You could do it with a video. If I'd had more time, I'd have put a video together for this. So that's something that it just can't do. And in fact, if you do that, if you think about it, that straight up jump corresponds to both infinite power would be required to do it, and you'd experience infinite acceleration. So you and the car would be flatter than a pancake if something like that happened. So I just want you to know this can't happen. It doesn't happen. That's just the way it is. And in fact, I say that on this next slide. The speed energy of a car must move smoothly with no jumps like that. It's just the way the world works. So what does all of this have to do with the world of the infinitesimally small? Well, electrons and other small particles don't behave smoothly. Their energy levels not only jump, the energy can't vary smoothly. Electrons simply jump from one energy level to another, and they do so instantaneously. So this is, they're doing what can't be done. You just can't, this can't happen, and yet that's exactly what electrons do. And in fact, they don't just move up like this. They can jump all around between different energy levels. Okay, so it can be up one, down a bunch of different. It happens instantaneously. It has to do with how the energy is passed along to them. And in fact, if we were to look at this, this would I haven't put the slide together, but the lowest energy level would correspond to actually a single lump, in our probability graph, it would have a single thing. This would correspond to 2. This energy level would correspond to 3. So it jumps between all those different energy levels. And not only does it jump, it can't exist in the intermediate energy levels. It can't even pass through them. What this means, I don't know. But this is, in fact, really where the name quantum physics has some of its genesis, is in the fact that in the small world, particles move with quanta, individual quanta. They don't move smoothly, change energy levels smoothly. Okay. So if you're, in wrapping things up, if you're feeling confused at this point, you should be. This is confusing stuff because small particles are very strange. They routinely move through places they have zero probability of being found, if in fact they can be said to move in any conventional sense at all. They may instead exist in I say it again, superposition of all possible states until the act of observation causes them to collapse into one particular state. Small particles also don't move smoothly through the spectrum of possible energies. Instead, they jump instantaneously between different fixed energy levels. Let's be honest, small particles aren't just strange, they do the impossible. They do things that make absolutely no sense. And I should point out that I've just touched upon the inexplicable weirdness quantum physics has to offer. If we had more and more time, more and more days, we could keep going. To me, the quantum world presents us with some of the best examples of realities beyond our comprehension. Our 3-pound brains are pretty impressive, but occasionally we run into situations that just don't compute. As I like to say, and many of you have heard me say before, reality is known through reason, yes, but can we know all reality through reason alone? And what happens as we reach ever further down into the world of the infinitesimally small? We've got a pretty good model of subatomic particles, the standard model that has leptons, bosons, and quarks that come in various flavors and colors. We'll save that for another day. But who's to say they're the end of the line? Who knows? Maybe it really is turtles all the way down. Thank you.
And now we'll have some questions. And if you want to ask a question, you can raise your hand, and I will make my way to you. But here.
Thanks, Eddie. Now I can see why you're on NPR. So my question is, this infinitesimal space, though, obviously composes this more normal space that we're talking about, right? So the car that's accelerating and cannot switch is composed of electrons. Mm-hmm. So how is it that you have basically this thing that's happening while this thing that it's composed of is not happening? How do we put the infinitesimal together with the reality that we do know?
There are a couple of things. The crossover from the very small to the very large, it gets a bit tricky as to where you're kind of crossing over. The other answer is that we are, this again, these are all philosophical questions so don't take it, in my mind, you just can't think about them too much because they're just too confusing. But the typical response would be that, in fact, the car is moving in discrete quantized energy levels. They're just so teeny tiny small that we can't see them, and for all practical purposes, we're moving continuously. We're moving smoothly.
Andy, I'm going to do a Lorentz transformation of a comment into a question. Uh-huh. Don't you need to consider the possibility that this looks incomprehensible just because your information is incomplete, not that it's something that defies logic?
No, in fact, I think it does defy logic. That's kind of my point. And again, that's my perspective. I've mentioned that before. I don't know how you can. I can't, based on anything that I know, explain the way these things happen. And I don't see that anything that we will learn will help us better understand things that just come up head to head with the way certain things we.
How about, for example, where the electron does not occupy that center position, that in fact the ends are tied together, that you've got a string, and the electron's traveling on the string, but it's coming around the other way.
There are all sorts of, and I know you think about these things too, there are all sorts of theories out there about these types of things, and you can posit things, but the reality is that, at least the state of the world as it is with physics, is that none of these potential solutions have been experimentally verified, and we're kind of stuck at this position where there is no experimental verification for it. I just speak my perspective. They're looking for good community speakers, Eric, so you can come up and talk about that.
Hey, Andy.
Jesse.
Wonderful talk. It was a lot of really good information. I'm curious, what are the applicable things that we're using in modern society where this kind of quantum and infinitesimal knowledge base is actually utilized, that like the things that we would use in everyday life?
That's a good question. I know there are some, I'm not that familiar with it. I think a large part of what we do is just to better understand the small world of physics. I'm sure there are applications. I know one that people talk about is quantum computing, which I've done some reading on, but I'm not well known. But quantum computing, if it does prove to be feasible, and I won't go into what it is, it would be amazing. It would just be a total game changer. So that would be one possibility.
I just have a comment.
Sure.
First, I want to thank you for all the pieces on NPR. Every time I look forward to hearing all your insights. It's wonderful.
Thank you.
And second, I want to mention something about the limit of reasoning, how we reason the world. And in the world of physics, to me, it seems easier. I take a I don't care approach. As long as the mathematics work it out, linear algebra is your friend. It's fine with me. I calculate probability. I'm a statistician, so training. I mean, in the medical world, though, in parallel, the people are using machine learning stuff. Physicians don't like the black box approach. There are millions of models evaluated at the same time, so you spit out the answer. But just like GPS, you use it, it works, and then you learn to trust that, right? So you trust the GPS to guide you. I know there will be kinks, somebody will fall into the ocean, because you follow GPS. But over time, as the training goes, the model will get better. That kind of chance of a mishap happen diminished. But and in medicine too, I can see, we can only reason so much, but this is more of a philosophical thing, how much, it's beyond our imagination. But, mathematics work out fine, it's the waveform.
Yeah, thank you. I'd love to talk to you about machine learning afterward. There's some issues on that too.
I thought you'd have a longer answer because I have to go across the room now. So I'll be brief then. There are a lot of thinkers out there like Deepak Chopra and the Episcopal apologist John Polkinghorne, who's a physicist, who, in my opinion, without being too mean, they take complications like those you've risen up and they kind of use them as this mask for really bad theology. And I'm curious what you make of some folks who they revel in mysteries in quantum theory and they kind of use that as a way to say, well, this is a good defense for my theology or my pet religion, and you can't question that because, look, quarks do weird things, so Brahma must be out there, right?
If you're using these types of observations for extrapolating to things that we can't prove in any way, shape, or form, that's wrong. And you do see people. If you go on the internet, anybody ever go on the internet? You'll see these long discussions about this type of stuff, frequently from younger people that are trying to come to terms with this stuff, and they put forward all sorts of crazy stuff. Maybe not theology, but the way it's really doing is this, that. You can't do that. You can't. At the same time, I think, as part of my overall discussion and talks I've given here has been about the fact that I really do believe there are things where our brains just aren't capable of dealing with it. I like to stop there. I like to just say, look, there may well be things that are real that we don't understand. What does that mean in my life? But I'm not going to go out and start pontificating about particular ways electrons move or why that has anything to do with God's existence.
In your diagram initially, it looked like a sine wave in a box, and you began to increase the number of peaks. Well, if you pass to the limit of an infinite number of peaks, would it disappear, or would it be infinite energy? I mean, is halfway to the top or the bottom? Where does it go?
It would correspond to infinite energy. One of the interesting things about mathematics, though, is we never let ourselves go to infinity. We let ourselves get as close as we want. In fact, the whole fundamental of calculus is based on the notion of a limit, which talks about as you get ever, ever closer. But even math doesn't let us go to infinity. So.
Okay, two things. The base assumption that that it exists in all superpositions at the same time, that sounded very much like Schrodinger's theory?
Yeah, yeah. What I was showing were actually solutions to the Schrodinger equation.
Okay, and then the second thing, we've been seeing 2D models and not 3D models, and I was wondering how that might look different.
The one-dimensional model is a lot easier to look at. And it's the simplest kind of, but three-dimensional models exist if you want to go online. In fact, one of the interesting things, and at the end I just decided not to put it in, but if you look at electrons in an atom, we have this picture of electrons going around the nucleus. They don't, again, it's the same type of thing. We can't follow them going around. We just can see where they show up. And they also show these same types of things, like an electron will spend half of its time on this side of the nucleus and half of its time on the other side of the nucleus, but it has a zero probability of passing in between. So if you go on and look, actually, even high school students get this, electron orbitals, not orbits, but orbitals. There's some beautiful pictures that show this exact same type of thing. So our weird electrons, as they go around as they form atoms, do the same type of this popping in and popping out type of thing. I shouldn't say popping in and popping out. We don't know. We don't know what they do.
Okay, and for our last question, I'm going to hand it off to the guy in the slick shirt.
Oh, thank you very much. So you showed the probability waves. Does that have anything to do with the wave-particle duality that you can find in the double-slit experiment, or are those different sorts of things?
No, they're all interconnected. I'm just trying to think what the direct. They're all interrelated. They all have related to this wave-particle duality of the world of small particles. But I couldn't make a direct step connection to it right now.
You're going to be at lunch?
I will be at lunch.
Okay. I've got a whole bunch more weird questions for you.
Good.
I didn't want to ask on a microphone, so thank you.
Thank you.